My name is Chris Montgomery. I'm a co-founder of Slice Engineering, a company headquartered in Gainesville, Florida, focused on the design and manufacture of hot extrusion components for fused filament fabrication printers, the type of printer that you see most commonly at rep festivals. I have a little bit longer to talk today than my presentation was allotted for originally, so I'm going to give a little bit of company background and a little pep talk first. So throughout 2016, I designed the Mosquito hot end and prototyped it in my garage on my milling machine. In February 2017, my friend Dan Baruch and I, Dan Baruch is over at the booth right now, we founded Slice Engineering specifically to bring the Mosquito hot end to market. Mosquito and its accessories launched in March of 2018 at ERRF. It launched in earnest about that time. We had it a little bit earlier. In January of 2019, Dan and I brought on board a third partner, a friend and owner of a machine shop in Indiana where all of our machining takes place and assembly. In the last few months, Slice moved into a real brick and mortar location. And we hired Javier, who's just joined us. He's a Florida Gators. He's a UF student. You could say Slice Engineering became a legitimate company maybe this month, maybe last month. Why did it take 3.5 years for us to get here? That's a question I ask myself sometimes. The truth is, Dan Baruch and I worked real jobs until we took a leap of faith to work for our company and not just on it. Now our business is growing steadily. We've relieved our production bottlenecks for the most part by purchasing machine tools. We hired 2 employees. We're on track to double the number of products in our portfolio by Christmas, and we have plans to triple the number of products in our portfolio by March of 2020 at ERRF. In retrospect, I only wish that we had taken the plunge sooner. And so I have a little unsolicited advice to any entrepreneurs in the crowd who are here with us at ERRF. If you're running your business by moonlight, and your judgment tells you there's a market for your product or service, I encourage you to take the same plunge if you can. At the end of each day, you'll be just as tired as before, but it'll be a better kind of tired. Okay, now on to the presentation. That's enough pep talk. Okay, first let me talk about why I designed Mosquito. This is this image is just a cross-section of our heat break. The units are millimeters. The first slide. This is the reason I designed Mosquito. I just wanted to change nozzles without fear of breaking a thermistor wire or loosening the mount. Or any other headaches associated with changing nozzles. I needed to change sizes of nozzles for different size prints and to get better interlayer strength or finer features. I needed to do that frequently. I found myself just designating printers to specific nozzle sizes, which isn't efficient if you have to print a lot of small parts. You want to just have all the printers doing the same part, get over with quickly. So that's all I was trying to do. Let me see if I can. Yep. Let's see if I can play. Oh, there we go. So that's it. That was the motivation. It didn't really have to do with thermodynamics or any performance-related aspects. So the title of this video is Evolution of the Hot End. So let me go into some hot end features that I've noticed just in my last 5 years of paying attention to FFF. Before that, I was engaged mostly in mostly machining, but SLS, SLA, DMLS especially, and just other technologies that were useful along the way in my orthopedics implant line of work. So traditional hot ends, those are the ones in the bottom row there. They're lined with PTFE. My first FDM printers had PTFE-based hot ends, and the problem with that is that the PTFE tube is subject to wear and thermal degradation as low as 240 degrees. I mean, you can soup up PTFE to get a little higher temperature, but certainly you're not going to print high-performance thermoplastics with those. That diagram up to the left is something I found on the internet, but it kind of gives an explanation. You have a long, kind of slower melt zone, and it's not ideal. The all-metal hot end, those two at the upper right are examples of all-metal hot ends, and that design has largely superseded the PTFE line hot ends for good reason. They have a sharp temperature gradient, and you get better precision out of them, the ones that are well made, and they don't have any temperature limitations to speak of when you're talking about thermoplastics. So they work very well, and really they left little to be desired. Again, my goal was to just have a simple nozzle change, one-handed with a torque wrench. So what I just showed you, those were two branches of evolution. You had the PTFE lined hot ends, you had the all-metal hot ends. Those are on two evolutionary branches. The Mosquito is sort of a second branch that's in parallel with the all-metal hot ends. It is a all-metal hot end. It is just it's different in that the heat break is not a structural element, and that's how we receive. That's how we get the benefit of torque resistance. So this is from left to right. This is the evolution of Mosquito itself. I started out with just standing off the hot block with tubes, but it was an inverted orientation on that first one. And the tube itself has no heat sink on it. It's just a very thin walled tube. All these generations use the same tube. And from left to right, the first two are the ones I milled in my garage. The first one didn't work so well. The second one, it worked very well. It left something to be desired when you're printing Voronoi style models. I'm not sure the right pronunciation of that word, but in any case, it's a very important type of modeling that perforates the outer skin of the part, and it has a lot of structural benefits if you're into like strength to weight ratio. Anyway, it's something that's important for a hot end to be able to do well, and That second prototype was not very good at that with PLA, unless you had really strong cooling. So the third prototype, I put a piece of adhesive-backed aluminum foil on it. So it's kind of pointing out of the screen there. You can't see it. There's a little flag on that heat break, and I found that solved the problem of the PLA Voronoi prints. It completely fixed it and could print without any fan installed at all. Just a desk fan pointed in the general work area was enough to cool that. And then the last iteration there is our current product. That's a Mosquito Magnum attached to the Montec BMGM. Here's some images of testing that third prototype. I'm sorry, this is actually the second prototype. So before the aluminum foil flag, testing runaway heating with a 60-watt heater. Get the hot block to about 570 and still air, 570 Celsius. And the top of the heat sink, depending on which measurement we're taking, it's 75, 80 Celsius. And you can see that even without any heat sink, the benefit of the thin wall tube, you can get a decently sharp temperature gradient shown in that thermal image to the right. So that was the second prototype. This is a video showing the third prototype, the one with the foil flag, printing a Voronoi beer out of PLA. And we've printed many different materials in this configuration. You can see there are no fans installed. The fans, this is on a craft bot. All the fans are removed. This was fun with a very expensive thermal camera that we borrowed that had, wasn't the right thermal camera for the job. We got a better one later for macro thermal images. But it was fun to see the FDM process from a thermal point of view. You can see the filament cooling. You can see why fans can be beneficial when you're trying to do overhangs and bridging and so forth. You need to get that red stuff to turn blue as quickly as you can in those scenarios. Okay, so let me go into the thermal benefit that you can have when your heat break is not a structural element. You're free to make that tube very thin walled. It doesn't need to be so thin walled, but if you can, if it's not taking the load, why not? And while you're at it, why not make the threaded bushing at the bottom and the radiator up top? Why not make those out of a highly conductive alloy? So that's what we've done. The image to the left is the standard Mosquito's heat break. The image to the right is a heat break that's soon to be released. It has basically the same geometry as a Mosquito Magnum's heat break down below, and then above it has the copper sleeve that's cooled with conduction or liquid, depending on the configuration of the base plate up top. So all the heat breaks have the same basic geometry, the same basic heat break zone in the middle. You've got two copper parts, separated by about 1.5 millimeters, and the 75 micron wall thickness strain hardened stainless steel tube connecting them. There's an added benefit of using a stainless steel hypodermic tube for a heat break, and that is the material itself is highly cold worked. It's very, very strong. 4 times the yield strength typically of a bar stock that is turned. And I'm going to mention this with respect to an upcoming product launch we have at the end of this presentation. It's relevant to that product in particular. The strength isn't quite as important for this product because, again, the heat break is unloaded on Mosquito, but it is important for our upcoming product. You can see that the thermal conductivity is very low. It's even a little bit lower because of the cold work. The copper alloy has an extreme thermal conductivity, much higher than we actually need It's also very resistant. The alloy we use is very resistant to creep at high temperatures. Which means that it's not going to soften in places where we have high pressure. For instance, like the bottom of the standoff tubes, which are under compression, it's not going to move on you at high temperatures. We started with one alloy, did some testing, and moved to another alloy for Mosquito, and we've had no trouble even at temperatures as high as, like I said, 570. So it's a pretty impressive alloy. An advantage of the copper is just that it can move heat quickly radially. So you see that we have efficient heat flow in to melt the filament. Whereas if this was a monolithic stainless steel part, then there is some restriction just due to the stainless steel's thermal conductivity, which again is 15, 17 watts per meter Kelvin versus 330 watts per meter Kelvin for the copper alloy. So that's the core of our hot end design is this style of heat break incorporating the strain hardened hypodermic stainless steel tube. The cross-sectional area of our tube is very low, so aside from the material properties, you can get much less heat flow up through the melt zone. Now, this is not to imply that you need a severely restricted heat flow up through the melt zone. The heat break down below is that's a cross-section of a typical all-metal heat break, and they work great. And that's the reason why I made the Mosquito was for the torque resistance. But there are some benefits to having it so thin walled. Again, that means the wall is thin also down below in the melt zone, and the copper can feed the heat to that thin walled tube without any restriction. That's not the bottleneck of the copper. So your bottleneck now is very thin, and you can boost the heat flow to the melt zone a little bit this way. Here's a thermal image, a thermal video of Mosquito Magnum heating up. This is without the ceramic insulator on it because I don't want it to obscure the image. But you can see that you get a very steep temperature gradient. This is with a 50 watt heater. And our fan. So the fan is blowing towards the camera. This is about how quickly you can expect it to heat up in a printer. This next image is just it's showing a Voronoi print of Mosquito that I was doing last week to confirm results of our 0.2 vanadium nozzle, which is our smallest nozzle. The reason I'm showing this is mainly so that you understand that these two craft bots they're identical craft bots. They're nothing special as far as the printer is concerned. They're not expensive printers. They had the PTFE lined hot ends. That's how they came. And the results of just switching to a higher quality hot end, an all metal hot end, drastically improved the results from the printer. And so when we launched our 0.2 nozzle, I thought this seems ridiculous. Why would you not go to stereolithography at this scale? And then when I actually started printing with the nozzle, I was surprised that wow, this really works well. It doesn't clog. And of course, you're not going to use fiber reinforced filaments at that size, but you can, with a wide range of thermoplastics, you'll get incredible results with small nozzles if you're having to print very fine resolution parts. So here's the print. This is out of PLA. Afterwards, I printed all kinds of plastics in the same part, got the same results. This is a macro image I took with the part still on the printer. That fine spider web stringing, this is like some 40-year-old PLA that came with the machine itself. Nothing fancy, again. That spider web string goes away with a 1-second blast from a heat gun. So this is how I prefer to get rid of the spider webs, not by extreme retraction settings. The retraction settings were 0.3 millimeters. So again, with a 0.2 nozzle. You notice the scale to the left, that's a millimeters. So we're really zoomed in here. You can get this kind of results from a good printer. This is a direct drive printer, not a geared extruder. The bottleneck for this printer was really the hot end. Here's some images of flow rate testing. We've had OEMs request flow rate information. This is my least favorite topic because it's so, I want to just put an asterisk, like 5 asterisks next to every statement, and I'll try to do that. I'll try to avoid the question when I get it, but then the OEMs they just want a number. So I'll give a number here. So this is an example of a zigzag. I've got a zigzag pattern with a print with a 0.8 nozzle, and basically just keep ramping up the speed 5 millimeters per second every 5 millimeters of height. So that's, as you can see, about 20 millimeter height part, and 2 of them. And what we find out of Mosquito Magnum is that with PLA, when the stars are aligned and the temperature in the environment is not too not too cold, and all the fans are turned off, and I boost the temperature really high, I can get 38 cubic millimeters per second out of a Mosquito Magnum, about 33 out of a Mosquito. Probably could get more out of Magnum if I was using a geared extruder and really pushing on the filament. But your results are going to be much different depending on your printer configuration, depending on what kind of interlayer bond strength you want, and how much die swell you can tolerate, a bunch of factors. So really, you just need to test with your configuration. I'm just giving this number because it's probably the most frequently asked question I get. It's the worst question. So some of the products we intend to launch in the future will be aimed to boost this flow rate, because there is a market for large format printers. You can tell some of the printers are getting bigger and bigger, and those printers, if you have something large to print, you really need that flow rate. So we'll accommodate this. One of the bottlenecks is just the amount of power controllers can handle, and of course we can always feed more heating power, but we want to be careful that the hobbyists are not going to overheat their control boards or have some other problems. So we're directing those products towards OEMs, but look for them in the future. There's certainly potential to go faster. Okay, so very important for hot end design is the nozzle. We like to cross-section stuff here at Slice. We cross-section our stuff, we cross-section everybody's stuff. What I will say about nozzles, the design quality variation, the material quality variation, and hardness variations that you see among nozzles, even within the same price range and the same target audience, they vary widely. So I encourage you to cross-section your nozzle and just see if it looks like it would be good in terms of flow. Some are much better than others. Some, you can see one, the very far right, that's marketed as an abrasion-resistant nozzle, and it's simply nickel-plated brass. And it will not take carbon fiber for, it won't even take 1 kilogram until it's damaged that. So you just need to understand what you're buying. I do see a pattern that the quality is getting better as time goes on with competition, but Very few people have a hardness tester. So just be wary of what you're buying. Also, if you see tungsten at nozzles advertised, make sure you're probably thinking that you want tungsten carbide, and that would be a good, not a bad choice. But you need to make sure that you're buying an actual tungsten carbide nozzle and not a tungsten alloy nozzle if that's what you think you're getting, because there's been a lot of confusion on forums. And unfortunately, one that was confused with tungsten carbide, it just had really poor tolerances. And so just make sure you know what you're getting. And tungsten carbide is a composite material. It's a cermet, whereas a tungsten alloy is just as a metal, and it's not especially hard compared to hardened steel or ruby tips or any of these other selections. So just read the fine print. Look at the tip of the nozzle. Make sure the hole is concentric with the flat as well. You'd be surprised how much. That's one of our quality metrics. We've made some off-center holes ourselves, and now we're on top of that, and that can affect your print quality. Okay. So how am I doing for 5 minutes? So this last video here is of our product that we hope to launch with our Kickstarter campaign. This will be our first open source product. So, thank you. It has to get launched on Kickstarter though, guys. It's not a sure thing yet, but we've prototyped it. It works well. It's called the Copperhead, and it belongs in the, when I said there are the 2 branches of all metal hot ends, it belongs in the first branch. It doesn't have the anti-torque features, but it does use the bimetallic heat break. The heat break is held on with a collar, so you can adjust the height a little bit if you need to for a dual extrusion printer. You can quickly take off the hot components if you want to decouple it for nozzle change, or to even just swap the whole hot assembly. And it has a few other bells and whistles, and like everything we make, everything we machine, it's machined here. It's machined in Indiana and assembled there, and it's just it's a good quality hot end, and it'll come in at a lower price point than Mosquito. We haven't figured out the price yet, but it has all the same temperature capabilities as Mosquito, and we hope that it'll be popular, especially among the RepRap community, because of the open source design. We'll publish under Creative Commons. I always get my terms mixed up. Attribution and share alike license, and full ASME compliant GD&T on the drawings. These are the same drawings that we send to our machine shop. You can make the product, and we encourage people to do that. We're not going to release those drawings until the Kickstarter gets funded, because we actually want to be the first on the market and make sure that we got all the bugs worked out before it's published, but it will be published. We also have a few more products which are part of the evolution. We started off in high temperature thermoplastics, where you don't really want to insulate the hot block, because there's no need to, because you're not blowing air on it. But with the RepRap community, PLA, PETG, these are very popular materials. You do need to blow air, so we have a Bridge Master line of products. They're accessories that go with the Mosquito and allow you to blow air. It's probably our most commonly requested accessory. It was just in line behind some other product development, and we're soon to release those products. I've got a sample right here of a very fancy silicone insulator. It's fire retardant, and a wrap for a nozzle which repels the plastic. Just can't stick to it because it's all PTFE, and it stays a little cooler than the nozzle when air's blowing on it. So we're going to circle back and take the hobby market back into consideration, now that we've been focused on the high temp materials for all this time. So I think I've got like 2 minutes. Maybe take one question. Let's see. Any questions? Yup. With details. So Kickstarter launch is Black Friday. So please back it because this is for the rep crowd. So we really want to bring it to market and have it in full production before Murph. That's our goal. Any questions from somebody who doesn't work for Slice Engineering? Sanjay?
Which was the nozzle in the very top left of the little montage?
Say again?
If we go back to the little montage of nozzles in that cross section. Yeah, that one.
This one?
Yeah, one right?
One right?
And yeah, top left.
Top left. The very top left, these guys. So,
Cheers.
I'm trying to remember which one is yours, Sanjay. I don't. It's been a while since I took that photo, but anyway, those two are good. So they passed all tests. Something to watch out for is like some of the nozzles have really long. The orifice diameter has a really long distance. So like from the molten plastic to the the big diameter till the exit. When that's really long and thin, it's not so good for anything. So that's something you can check out with a Dremel tool on your own. Yes, sir.
Just a quick question and follow-up to what Sanjay just asked. Do you publish information on this stuff anywhere?
Like the performance data, for instance, the flow rate information I hate to give out?
That, and then also like the cross-section information about the different nozzles.
No, I mean, I wouldn't even identify whose nozzles these are, so no, I guess is the answer to that. It's just for our internal studies to understand what our competition is doing and where do we stand. I think my time is up. Thank you, guys.